Hello folks and welcome back to Skybound on the Ground with Michael Lombard. My name is Michael Lombard. We are learning about aircraft systems. Last time we learned about how an engine works, the basic principles of the four-stroke engine. We also learned about constant speed propellers. And now we're going to learn about snowmen. Well, not quite. But you might be wondering why we have Mr. Pilot Snowman here and also Beanie and the sunglasses. Are we going to learn about skiing today? No, we are learning about something really cool, a cool application of aerodynamic principle that we learned back in aerodynamics class just a few lessons ago, and how this helps our engine to operate, but it's so cool that it can also potentially freeze the inside of our engines. Wow, what's that? Well, let's take a look at it. So we are going to be learning about induction systems to get going here. Induction systems are the system that you use to supply the engine with fuel and air. So there are two basic types of induction systems that you might have on an airplane. There is the carburetor, and then there is the fuel injection type. Carburetor is really the old school way of doing things, but we still have airplanes that use that because we fly old airplanes. They are well maintained, so don't worry about that. But the carburetor is really elegant in its design because it doesn't require a fuel pump, whereas you have to have a fuel pump for a fuel-injected engine. So let's take a look at how it works. It's a really cool principle. And so this is where we're getting our air. We have the air intake over here. Somewhere over here is the outside world. And so that's the outside air. And that'll be coming in through some type of a filter through the air intake. And then, of course, you have over here, remember inside the intake you have the intake manifold, and you have this butterfly valve, which is the throttle valve, or the throttle plate. And so if you have your throttle all the way open, it's going to allow all the air to go on through to the engine. And so this goes to the engine. Well, somewhere along the way, we need to have fuel going to the engine as well. You have to have a mixture of fuel and air in order to burn in the cylinders and provide power to the crankshaft. So how do we provide that fuel? Well, we can have a fuel jet stick up through here. So we're going to have this fuel jet with a nozzle on the end. And so we'll have fuel in there. But remember, we want to have this designed without a fuel pump. How are we going to get that fuel sprayed out into the airstream without having something to pump it out? This is where we apply Mr. Bernoulli's principle of whatever he called it. It's Bernoulli's principle. That's what it is. So remember what Bernoulli discovered. He found out that when you speed up a fluid, like a gas or a liquid, when you speed it up, the pressure of the fluid has a corresponding decrease. So you have this, if you put a narrow spot inside a tube, we call that a venturi, and that narrow spot has the effect of speeding up the air that's rushing through there. And when it goes through that narrow neck right there, you have a decrease in pressure. And so suddenly, you're basically sucking the fuel straight out of this fuel nozzle right here, out of the discharge nozzle. So fuel is able to go, and as it comes out, it gets sucked out, it gets evaporated, it's vaporized into the airstream, and then it goes on to the engine where it's burned. So it's such an elegant design that you don't have to use any fuel pump. And so that's what I thought was really cool about that. But the problem is it can be too cool, because what happens is if you decrease the pressure of a gas, it also decreases its temperature. So over here you have air that's coming in that's say it's 70 degrees Fahrenheit. Nice warm day outside. It comes into the neck of the venturi, and suddenly the pressure drops just like that. And what happens to the temperature of the air? Temperature also drops. Well, say the temperature dropped to 25 degrees Fahrenheit or something. While the air that came in if it had a high humidity, that means as the pressure drops and the temperature drops, that air can't hold all that moisture anymore, and so the moisture condenses, and now because you've cooled that air, and it's also cooled the parts around here, you've cooled that air to below freezing, and all that moisture, oh, it's so cool in here, we're just going to freeze onto the inside of the engine, the inside of the intake here. Going to freeze onto the throttle plate, and you get this phenomena called carburetor icing. And what do you think this does to your engine? I mean, you know, I sometimes get ice inside my fridge. That doesn't make the whole thing quit. But if you get ice forming inside here, that is the same almost as closing your throttle. You're starting to restrict the opening, and it can actually get so bad that it basically completely clogs it all the way up. And then your engine is not getting any air or fuel, and so your engine is going to quit. That's not a good situation to have while you're flying around. So what are we going to do about this? Well, we could go to a fuel-injected engine because it doesn't have as high a tendency to have such a problem like this. But we want to have our carbureted engine because we don't have to use a fuel pump for it, and it's just very easy and simple to make. So what designers came up with was a workaround. They decided they would have a way they would supply preheated air to the engine, and so you use carburetor heat, and just call it carb heat for short. And so via an alternate means, instead of air coming straight through the intake, you're actually feeding preheated air from another part from inside the engine compartment. And so that air comes in, and because it's nice and warm, it doesn't have the tendency to, when the temperature drops, it doesn't drop below freezing. And then also, if you had ice in there already, it starts melting it away. And so the carburetor heat is useful for preventing icing if you have icing conditions, or removing icing if you happen to get icing in your engine. There's a disadvantage to having the carb heat on, and that is when air is warmer, it's less dense. So you're not going to be supplying your engine with the maximum density air that you could be giving it, so the engine is not going to perform as well. You've also messed up the ratio between the density of fuel and the density of fuel and the density of air that's going to the engine, because you have to have a specific ratio. And so if the air is less dense, you have less molecules, and you have correspondingly more molecules of fuel to the amount of air that you have. So your engine is going to be running a little bit rougher that way. But this is just, once again, this is just for cases where you can't, where you're flying along and you start getting icing, so you just want to prevent that icing or melt the ice that's developing inside your engine. How do you detect if you're getting carburetor icing? It'll be very simple. If you're flying a fixed pitch propeller, remember you're only going to have an RPM gauge, so your RPM gauge is going to start indicating less because you're going to start losing power from your engine. If you have a constant speed propeller, while your prop governor is going to be doing its job of changing the blade angles to try to maintain that RPM. So the first thing you're going to notice is, instead of a drop of RPM, you're going to notice a drop in manifold pressure, because it's the same thing as closing off your throttle up here. You're restricting the flow, and so it's going to create a little bit of vacuum on this side, and so the manifold pressure is going to be less than what it could be. Alright, so when you apply carburetor heat, you're going to also notice some interesting things if you do happen to have ice inside the assembly right here. What will happen is that ice starts melting, and so now you're feeding water into your cylinders. So the engine's going to run rough for a few moments, and don't worry, it's going to improve, and then you should have a steady increase of RPM back to something that was higher than what you had right before you turned on the carb heat. But if you continue running with carb heat, like I said, that's going to decrease your performance. Don't try to take off with carb heat on, but there is one situation where you do put carb heat on even if you don't have any icing going on, and that's usually during a landing approach. Because when you bring your engine all the way to idle, you're not producing as much heat with the engine, and so it's not going to it's going to be a lot more prone to ice forming inside here. So we just take we just turn on the carb heat as a preventive measure, because an ounce of prevention is definitely worth a pound of cure in this case. We don't want to have our engine quitting on us while we are trying to make it to the runway. Okay, so that is carburetor heat for you. There's also other disadvantages to having a carburetor aside from just the icing, and that's just the fact that the fuel that's coming out here is at low pressure, and it's hard to vaporize it completely. So you're not gonna have complete vaporization. That means the fuel isn't gonna mix evenly with the air, and so the engine performance won't be as efficient as it could be. Let's take a look a little bit more at what this carburetor looks like, the rest of it. This is actually called a float type carburetor, and that's because we have a chamber over here. So this is the chamber where it gets the fuel from. Okay, so here's our chamber, and well, first of all, here, let me modify my representation here slightly. First of all, we need to have a way of controlling how much fuel is able to go out of that fuel discharge up here. And so we actually have a needle valve. So here's our needle, and this is hooked up to a control in the cockpit. It's called the mixture control. And so this over here will, based on if you shove it down, it will either you can completely close off the supply of fuel. You have fuel in here. And so if you completely shut off that supply, that's actually how we turn off the engine. We just push the mixture, we pull the mixture control in the cockpit all the way out, and that shoves this needle all the way down into the hole right there. Now, if you have it partially in, that's going to restrict the flow, so the fuel will go out slower. And the reason we want to do that is if we go up to higher altitude, remember, you're going to have less air density, and so you need to adjust the amount of fuel that's going into the engine. You're going to have to decrease your fuel supply as well. And so that's called leaning the mixture. You're going to make sure that you keep the ratio of air molecules to fuel molecules at its correct ratio. Otherwise, you're going to start losing engine power. And so we adjust the mixture. You will reduce the amount of fuel going into the intake, and so that will be leaning the mixture. If you increase the amount of fuel, that's enriching the mixture. Enriching, is that a word? Anyway, enriching the mixture. So that's the mixture control right there. And just a little bit of other considerations for actually operating. When you go up to altitude, you need to lean your mixture. And then when you come back down, you need to make sure you enrich the mixture. Otherwise, you can have the problem of running it too lean, and you can have detonation, which is something we're going to learn about later on. And if you don't lean your mixture when you go up higher, you have all this extra fuel that's going into the cylinders, it's unburned. It doesn't have complete combustion, and it leaves these carbon deposits especially on the spark plug, so you get spark plug fouling, and it's not really good for your motor right there, and your engine is going to run rough as a result. So that's a useful control right there, the mixture control, and that's the mixture needle valve. And I said this is a float type chamber, a float type carburetor, because inside this chamber is a float, and the float is basically like the float inside your toilet tank. And the reason you have that there is when you flush the toilet, that tank gets depleted, and so the float drops down, and it opens up a valve to start pouring water back into the tank so that it'll be ready to flush again next time. Same thing here. We need fuel to be inside this chamber. We don't want too much, but so when this you have this attached to a valve, when the fuel level drops, the float goes down and it opens up the valve, and more fuel is able to fill up the chamber. Of course, you can see this is going to have some limitations. You can't fly the airplane upside down because that will just mess the whole thing up. And you can't do, also wild maneuvering. If you're keeping the airplane coordinated, then that's fine. But yeah, just keep that in mind. So that's the float type carburetor. You might still have this you might still have a carburetor whereby you squirt fuel into the airstream, and this could be a pressure type carburetor, but you have to have a fuel pump for that. And in that case, pressure type carburetors are less prone to icing because you actually put the discharge jet on this side over here, and you're not using a venturi to speed things up because you have something to squirt the fuel into the airstream already. This is our float type carburetor, and that is how it works. Now what about fuel injection? Well, people got a little bit tired of having to always turn on the carburetor heat when you're on landing approach, having to worry about having icing conditions. Icing conditions are especially prevalent. You have especially high risk when the temperature is between 20 and 70 degrees Fahrenheit and you have high humidity, because that's when if the temperature drops, then you're going to, that's going to cause the icing inside the engine. So they got tired of that. They decided they want to have something that has better performance, and so they made a fuel injection system. So fuel injection is it's very nice. Let's take a look at it here. You have the let's see here. I'm just looking at my notes and my drawings. Oh yeah, okay. Okay, so here is your cylinders, and we're looking at it from the top view. And so fuel injection, it's a very simple concept. You just squirt fuel directly into the cylinder as it's doing its intake stroke, and so instead of having to worry about mixing it into the airflow as it's coming in and all that stuff, you just go right to where the action is happening and you squirt the fuel right into the cylinder right there. So you have this intake, this fuel line and these discharge nozzles onto each cylinder. And you have to have a place where it's all coming from, so you'll have this central fuel distributor right there. It looks kind of like a spider, doesn't it? Okay, and so from the fuel distributor, this is where you have to have an engine pump, a engine-driven fuel pump, because you have to be able to have something that squirts the fuel, that pushes it into the cylinders. You have to have something to supply the pressure. So you have a pump right there. And actually, let me back up. Before we go to the pump, we actually have a device right here that is the fuel air control unit. It senses how much air is actually coming in the air intake and going to the engine based on how much your throttle is open. And so it senses that airflow, and then it will allow a corresponding amount of fuel to be fed out to the fuel distributor. So that's an important thing, because if you have it off, it's going to affect your engine performance. So you need to be metering out fuel in proportion to the amount of air that's going to the engine. Thankfully, you don't have to do that yourself. The fuel air control unit does that. Okay, so before the fuel air control unit, then you have the engine-driven fuel pump. And this is driven by the engine. That's why it's called an engine-driven fuel pump. Now, just in case the engine-driven fuel pump fails, we have an alternate means of getting fuel to the engine, because if we don't have a way of getting fuel to the engine, we have no way of having the engine run, and our engine will quit. So we have an auxiliary pump, and that's usually run off of off of the electrical power, and you can run it off the battery. And we also use this when we're starting up the engine, because obviously the engine's not running, so it won't turn the pump. And then of course you have, so that's goes on an alternate pathway right there. And then that's our little mini fuel tank. It's a lot bigger than that, but that's just a representation. So that's fuel injection. Fuel injection has the advantage that it's not as prone to induction icing like we had with the carburetor system, and it's also able to precisely put out just the right mixture into the cylinders, and you're going to have a better fuel distribution, so one cylinder isn't going to be getting more than the other one, and you'll have better fuel flow, It's easier in cold starts. When the engine is cold, it's also going to be quicker with throttle response. Disadvantages is that it's actually hard with hot starts. And that's because of these fuel lines that are sitting above the hot engine. If you shut off the engine, you don't have any breeze going through the engine compartment anymore, cooling things off. And so what can happen is the fuel sitting in the lines starts to boil, and it forms these vapor bubbles in there. And when you try to restart the engine, those bubbles block the fuel from flowing into the engine. And so it can make it quite a challenge to get that engine going again. You can also still have the same problem while you're doing ground operations because, again, you don't have a lot of air flowing over the inside of inside your engine compartment, and so once again, if it's hot temperatures in there, it'll boil that fuel and cause vapor lock, and so that can also cause problems while you're on the ground if you're not keeping that engine cool. If you happen to be in the air and somehow your engine had fuel starvation where the supply of fuel to the engine was interrupted, you can get air bubbles going in there, and you can also have the same vapor lock problem going on. So those are disadvantages of fuel injection, but generally fuel injection is a really good way to go because you don't have that icing problem and you get better engine performance. Now, I talked about keeping things cool. How do we keep an engine cool? You can have air flowing over it, and that's what we call air-cooled engines. Well, that's the external cooling. What about the internal parts of the engine? Well, you know about oil. That provides lubrication. It also provides cooling for the engine. Let's take a look here. So we're going to take a look at the side of the engine and just take a look at a very simple diagram of what the oil system looks like. So once again, those are the cylinder heads right there. So we're looking at the side. Let's say that's part of the propeller hub or whatever. Okay, so there is a reservoir of oil down here, and we call this the oil sump. And so what's happening is you have oil circulating inside the engine, and so it's going around there, and then eventually drips down to the bottom here, comes through a little screen thing, and drips down into the oil sump. So now you got all this hot oil that has removed heat from the engine, from the inside of the engine, and then we gotta pump it out. So we have an engine-driven oil pump. So the oil pump pumps this hot oil out here, and it pumps it out eventually to an oil cooler and filter. And so the oil comes in here, gets to cool down, gets filtered, and then it comes on its way out. And then it just gets pumped back to the engine, where it can do its thing of lubrication and removing heat, and then going back in, and so it just cycles on back and forth. You'll have a couple gauges that are hooked up to the system to tell you kind of what's going on. One gauge is the, wow, keep on having to use this eraser. One gauge is the temperature gauge, and so, you know, that'll tell you how hot your oil temperature is, and that can give you an indirect indication of how hot your engine actually is. And then over here, you'll also have a oil pressure gauge, and that's important to tell you if the pressure, if enough oil is being supplied to the engine. If your oil pressure is dropping while you're in flight, what's probably also going to happen is your temperature is going to go up. But if you lose oil pressure, that's a bad thing, because if you run an engine without oil, what happens to that engine? It seizes. And so you're going to want to get on the ground as soon as possible if you start seeing your oil temperature peaking and your oil pressure dropping. And, oh wow, I hear a very noisy helicopter going by. Distractions, distractions, distractions. Okay, back to talking about flying instead of watching other people doing it. Oil temperature, if it just goes, if the oil temperature starts going up and maybe nothing's happening to your oil pressure gauge, there's other things that could be going on. You could have like a clogged oil line somewhere. You could have you could have low oil pressure, low oil level. You could have a blocked cooler, and or it could just be a bad gauge as well. But you can't just dismiss it as a bad gauge. You want to land and get it checked out. So that's our oil system. Just a very simple representation of it. You'll learn about wet sump and dry sump. This is a wet sump system where the oil reservoir is actually right underneath the engine. The dry sump is where you have the oil reservoir in some other place and then you pump it into the engine and stuff. It's a little bit more complex. So that's how we keep the engine cool on the inside. How do we keep it cool on the outside? Yeah, that's right. We use air cooling. So let's just draw our engine again here. So here's our engine, and there's the outside of the airplane. And so we have air that's flowing in, and you've probably seen that you'll see these fin-looking things on engines, on the cylinders and stuff. And as the air is flowing over that, those fins help by cooling it because you have more surface area. So it's kind of like the big ears on an elephant. That's how it dissipates heat and gets rid of it while it's out there under the African sun. And so same principle over here. The more surface area you got, you're going to be able to remove heat better. And so they put these fins on top of the cylinders to help dissipate heat. So you have air from the outside flowing in here and flows over the engine, and then it has some way of getting outside of the engine compartment. Keeping your engine cool is very important because if you get it overheated, you're going to have problems like detonation, which we're going to explore a little bit more in the next lesson. But that's basically where the fuel and air inside the engine explodes instead of just burning smoothly and evenly. And that will actually contribute to the engine overheating even more, and you get damage inside the engine. So you want to make sure you avoid that. There are several flight situations where your airplane is going to be more prone to overheating, and that's when you're taking off because you're at high engine power and low airspeed. It can also be while you're taxiing along, and also just if you're taking off again because you didn't land, so you're doing a go-around. So whenever the airplane is at high power settings and low airspeed, you're not going to have much of this cooling air flowing through the engine, and so it's going to be more prone to overheating. There's ways that you can reduce the heat, and that is, well, increase your airspeed, or you can reduce your power, or do both if you can. Another way is to actually enrich your mixture. So have more fuel that's going into the engine. It's kind of weird, but the unburned fuel that comes back out actually helps remove heat. So it's kind of a messy way of doing things. No, you won't see fuel dripping out the exhaust pipes, but it will be kind of, it will be evaporated fuel. So that's one way to increase cooling. You might also have something called cowl flaps, and that's not cow, but cowl flaps. And so it's these flaps that you can open up to help get more of that heat outside of the engine compartment. Alright, so that is internal cooling. We also have to do something like, we have to remove exhaust from the engine because that produces, the engine produces exhaust. We don't want to have that hanging around, so we have an exhaust pipe just like on a car. And so let's take a quick look at the exhaust system. So once again, here's our cylinders, and they have these exhaust pipes coming off them. And that'll go to a muffler. Whoops. And then that'll go out to the outside world. Now the muffler will have something over it, and you'll have this shroud over it, and the shroud is vented to the cockpit. So The nice thing about this is that you can take advantage of this hot exhaust gas that's coming out. It's heating up the muffler, the metal up there, and so that will heat up the air that's inside the shroud. And if you want to get some heat in the cockpit, you can just open up a vent right here. Just open up a vent and let hot air into the cockpit, and you can warm your little toes right there. So that's how you actually get heat inside light airplanes, and that's from the exhaust. You just got to make sure that maintenance is done regularly on your plane and that there's no holes inside your exhaust system, because otherwise you can get carbon monoxide coming into your cabin. And what does carbon monoxide do to you? Basically knocks you out eventually, and that's not a good thing for a pilot to experience, because you could be out for a very long time. So make sure you don't have any holes in your exhaust system. Now, wouldn't it be nice if we could somehow take advantage of all this hot gas that's going out? I mean, it's like it's going to waste. We could do a little bit more with it than just heat our toes, right? This is where turbochargers come in. And so people have done just that. They have exploited the hot gas that's coming out, the hot exhaust. And so the way they do it is by running this. Let's just erase all this here. So running this and putting a turbine inside the exhaust tube, inside the exhaust pipe. So you have this turbine that starts spinning up as the hot gas goes through, and then it goes out that way. So you spin up this turbine, and then you put a shaft on the turbine, and on the end of the shaft you put this impeller. It's basically kind of like a propeller type thing, and that spins as well. So the turbine is spinning, and then what they do is the air that's coming in from the outside, they hook this up to the they put the impeller inside the air intake, and what that does is it compresses the air. It becomes an air compressor. So we have our outside air coming in the air intake, and as the turbine is spinning up because of the hot exhaust gas that's being vented off the engine, that is turning this impeller right here, and that is compressing the air. And so that is feeding the engine with thicker air. This is very useful if you're going up to altitude, or up to altitude that's anything higher than sea level. Because remember, what happens is as you start going up, air density decreases. And if air density decreases, you're going to have to reduce the amount of fuel you're supplying to the engine, and you're just going to have less power output total. Well, what if you could have sea level pressure being fed to your engine all the way up to who knows how high you want to go? That's exactly what a turbocharger is able to do, because it compresses the air coming in, and so instead of air pressure being at 25 inches of mercury at like 5,000 feet, you're going to be having sea level pressure air inside here. That is wonderful. While you can have too much of a good thing, there's always a possibility of having too much of a good thing, because this can get spinning really fast. It can actually overboost, and you can provide pressure. You can provide air that's under too much pressure to the engine, and that will cause detonation. So we don't want to have that happen. We have what's called a waste gate, and so this is a relief valve. As the exhaust is coming through here, we can actually bypass that turbine completely by just letting it go out this way. And excuse my messy drawings, I just get excited. So we can have it bypass the turbine, and so instead of turning that turbine up really fast and having the impeller push all this super compressed air to the engine, we can just have it bypass completely. Okay, so we have a valve in here to control what's going on. It's called the wastegate valve, and if we close that valve, all the air is going to go through the turbine. If we have that valve all the way open, none of the air is going to go through the turbine. So you start out on the ground during takeoff, and say you're at sea level altitude, so you're not going to need anything extra. You're going to have full power. So you have the wastegate all the way open. You're not going to really be turning that turbine. But as you start going higher, that wastegate will start closing, and you'll have more and more air being directed past that turbine to power up the impeller and supply greater pressure out of the engine. As you finally get up to a high enough altitude, this gate will be completely closed, and now you'll be venting all the gas through that turbine. If you keep on going higher, you've basically passed the critical altitude of the engine, and so anything higher than that, you're going to start losing power on the engine because you're not able to supply sea level pressure air anymore. So that is the wastegate. The wastegate is usually controlled automatically, but you might have a manual control from the cockpit. You just learn how to use it, and you just learn how to make sure that you don't close that wastegate completely when you're down low to prevent overboosting. You got to also make sure that your oil system is working properly, because this thing is spinning like crazy. It is actually spinning upwards of 80,000 revolutions per minute, and so that is reliant on a very good oil lubrication. You need to have that oil circulating through there, otherwise that thing will start coming to bits. So make sure your oil system is working properly. And that's turbochargers for you. You might have heard of superchargers, and it's a very similar system, except instead of using exhaust gas to power the impeller, it actually uses an engine-driven pump. An engine-driven it is engine-driven, that compressor right there. And it's actually, in principle, less efficient than using the exhaust gas, because otherwise you're just throwing away exhaust, and we need to use that. We can use that somehow, but with the supercharger, you're actually taking more power from the engine to drive that impeller. So that's the supercharger. You and I aren't going to be flying supercharged airplanes, but just so you know, they're capable, and they're actually mostly designed to push in air at higher than sea level pressure. But you have to have a high performance engine for that. Alright, so that's turbochargers, and that's cool stuff. I've gotten to fly a turbocharged airplane. Got about 30 hours in a Cessna 182 that has a turbocharger on it. You probably won't be training in a turbocharged airplane, but once you get your license, you might move up into that and get your high performance endorsement. Now, let's really quickly talk about something called FADEC, Full Authority Digital Engine Control. We know that we have in the cockpit, we have a throttle, and so that's how we control how much power the engine is going to put out. And we also have, if we have a constant speed propeller, we have another knob. So these are like push rods that you push into the firewall. We might have another knob called for the prop. So we'll have the throttle, and then you have a third knob, and you'll always have this one. This is the mixture. And remember from our discussion of the float type carburetor, the mixture determines how much fuel is actually being supplied to the engine, and you need to lean out that mixture when you go higher, so that you don't provide too much fuel because you're getting less air. So you're going to have these three controls. You're always changing them for something that's going on in the flight. And some people got very tired of that, and so they eliminated that, and they just had one single control, and they just have a computer take care of everything else. And this is called Full Authority Digital Engine Control. And it's pretty nice, because now you don't have to worry about adjusting the mixture, you don't have to worry about adjusting the RPM. It does everything for you. This just acts like a throttle. I want to go up, I want to go forward, I want to go full power, just push that puppy in, and we'll start going, and it controls the timing, the precise fuel distribution, and exactly how much fuel is going to get supplied to each cylinder, the exact amount of, the exact mixture, and it'll change the RPM setting for the precise, efficient RPM, for whatever speed you're going at. It does it all. But you got to make sure that you have a power supply for that, because it's a computer, so it's electronically operated. And so what they'll do is they'll have it'll run off the airplane's electrical system, and it'll have a backup power supply just in case the electrical system goes south. It also will probably have 2 channels by which it operates, 2 exactly redundant channels, so that if one circuit goes bad or something, it'll be sending the exact same signals to the other channel. Because if this thing fails, your engine also fails, which is not a good thing. So this is all about our engine systems and cooling and carburation and all that stuff. This has been really fun. I really enjoyed preparing this lesson. And next lesson we're going to be wrapping up aircraft systems. We're going to learn about, the fuel system, how we can actually make that engine run, and how we can get that puppy fired up. So join me next time for more Skybound on the Ground.